Proof Techniques 7. Logical structures of proofs of implications. When we have if and only if statement, the statement has double implications. 1. If, then P. 2. If P, then Q. So when we have a statement, if and only if to prove, then we need to prove these two statements. So here is an example. Prove that an integer a is an odd integer if and only if a can be written as a sum of two consecutive integers. So this is a if and only if statement. So we need to prove two implications. One, we prove if a is an odd integer, then a is a sum. A is the sum of two consecutive integers. So now then you will look at this one. So a is an odd integer. What does that mean? So we mentioned that before, how to write an odd integer, right? So based on this one, you can say, because a is an odd integer, so a can be written as 2k plus 1. But now 2k plus 1 can be written as k plus k, right? That's 2k. So therefore, and use the associative law, you can say k plus, and then you can do k plus 1. So k is an integer, then k plus 1 is the next consecutive integer because it's 1 larger than k, right? So k plus 1 is consecutive. So a is the sum of consecutive integers. We demonstrate that, okay? And then the second part, we need to prove if a is the sum of consecutive integers, then a is an odd integer. So now remember how we express two consecutive integers. So that k and k plus 1 be consecutive integers. So then we talk about the sum. That means k plus 1. And now by associative law, you can do k plus k, that gives you 2k plus 1. And this is an odd integer, right? Because any integer in this format is an odd integer, which is an odd integer. So we proved the second case. Therefore, we proved the statement. So a is an odd integer if and only if a is the sum of two consecutive integers. So that's the proof for if and only if. And now Let's look at another case. Second example, that a be an integer. Prove that the following statements are equivalent. 1, a is an odd integer. 2, a square is an odd integer. 3, a is the sum of two consecutive integers. We proved this 3 statements in some way. So if you look at what we mean by equivalent, that means if you start from a, if you say a is an odd integer, then that you can make a conclusion that a square is an odd integer. And if a square is an odd integer, you can prove that then a can be written as the sum of 2 consecutive integers. Just now we prove if only if, so this we also know it is true. So typically when you have equivalent statements, you would go from 1 and then you prove 2. Then assuming 2 is true, then you will prove 3 and then 3 to 1. So that is equivalent. But you could also say, you depend on your preference. You may also say, okay, from 1, if a is an odd integer, then you can prove 3, and we did just now, is the sum of 2 consecutive integers. So then from 3, you can prove that if a is a sum of 2 consecutive integers, then a square is an odd number. And then from 2 to 1, you can also go any way you like to. Okay, so as long as you can prove from one to the other, then that is equivalent statement. So in this case, because we did some proofs before involving these statements, so we would choose this one. Okay, so we prove from 1 to 3. So that is, if a is an odd integer, then a is the sum of 2 consecutive integers. So this one we just did, and we do not need to repeat here. And then from 3 to 2. So 3 is a is the sum of 2 consecutive integers, then a square is an odd integer. So we have the assumption that a is the sum of 2 consecutive integers. So therefore, we can say, you know how to express 2 consecutive integers, right? So if k is an integer, then k plus 1 is the next integer. So these two are consecutive integers. So they say a is the sum, so k plus 1, which is 2k plus 1, right? So that is a. And then we want to show a squared is an odd integer. So you just squared it. So a squared equals 2k plus 1 squared. And now this, you can FOIL it, right? So 2k plus 1 times 2k plus 1 when you FOIL it. So 2k times 2k, this gives you 4k squared. And then this times 1, that gives you 2k. And then you take 1 times 2k, you get another 2k, then 1 times 1 is 1. So if we want to show this is a odd integer, then we need to write it in the format as 2m plus 1, right? Because this is a general, format of an odd integer. So that's pretty easy. You need to keep 1, and then you just, for this group, you just factor 2, and then that becomes 2k squared plus k, and then actually plus another k. So that will be this plus 1, right? So this would be the m. So it's in the format of a integer. So a is an odd integer, right? So we prove from 3 to 2, and then finally we circle back to 2 to 1. So from 2 to 1, statement 2 is a squared is an odd integer, okay? If a squared is an odd integer, then a is an odd integer. So we did this one before, and we skipped this one. So this for your review. Okay. So if we have equivalent statements, then you can go anyway. But sometimes you can also say, I can start from 2, and then we prove 3, and then we prove 3 to 1, then we 1 to 2. So it does not matter how you, start to prove equivalent conditions. So that is one case of implication, if and only if. The second case about implication, P to Q. We mentioned that before. If P is false, then any Q is true. Okay, so when we talk about the truth table, remember? Okay, so let's look at what we mean here by an example. So prove that if n is the largest natural number, then n is 1. You know there's no largest natural number. So this statement actually, that n is the largest natural number, this statement is actually false. So because this statement is false, then the result, any result can be true. Why? Let's prove this. Okay. So by contradiction, if the result is not true, so say by contradiction, that n, so by contradiction, assume n is not equal to 1. So if n is not equal to 1, then you can take n plus 1. So, and then n plus 1 is bigger than n, right? But you assume n is the largest one, but then you find a larger one. So this contradicts to n is the largest natural number, because you assume n is the the largest one, but however, if we take n plus 1, then we find a larger number than n. So therefore, n is not if it's not the largest, so that is a contradiction. So therefore, the contradiction means our assumption is not correct. So n is 1. Okay. Of course, you know. So that's why in logic, if the p is not true, then any consequence can be true. And that, so if we have something to prove, and if we know the statement is not true, the p is not true, then any q is true. Similarly, you can prove the following exercise. So for example, you can prove if n is the largest natural number, then n is unique. Or second one, if n is the largest natural number, then it is 5. Of course, you know 5 is not the largest, but because the assumption is wrong, therefore any consequence, any conclusion can be true. So that is the end of this topic.